All right, AP Chemistry folks, this is going to be our Unit 8 work for Chapter 13, Chemical Kinetics. So we have the 4 different learning objectives here. The bulk of it comes from that second learning objective, the rate law and integrated rate law. Now, as I go through this, there's going to be a lot of repeats of practice, the same concept over and over again. And so I'm probably not going to go over every single question here. So if it comes at the end where there was a problem that you weren't sure what to do or you got confused with, and it's not one that I worked out for you here, please make sure that you come in and see me. I'll be more than happy to go over that problem with you individually. All right, so not a lot of explanation work in this packet. Now that doesn't mean that there isn't going to be explanation work on the quizzes. It just means that there'll be definitely less and a lot less of my handwriting or my red type. You'll see here a lot more of me writing things. So the first one is distinguish between those two different rates, the average and instantaneous. The average is going to be the rate over a specific amount of time, where the instantaneous is the rate at an exact moment in time. And if we were to do some kind of a curve and look at how that works, we could do what's called the slope of the tangent and figure out the instantaneous rate right there. Now, that is not a math thing that we need to be able to do for this, but that's how the instantaneous rate is determined. Now, it's somewhat, it's the analogy that we use in class is driving somewhere. So if you were to drive, say, 360 miles in 6 hours, you'd be driving 60 miles per hour. And that would be the average rate. Where the instantaneous rate could be different whether or not you're stopping for food, gas, or you're passing someone, something like that. So the instantaneous rate is different, it's just like your instantaneous speed is different than the average. So there's that. All right, I didn't highlight this one in red, but two different reactions, one that's slow, one that's fast. Combustion reactions are almost always going to be very fast reactions, where like photosynthesis or rust is a slow reaction. Rate expressions, we have two different ones here. So we have my fault. It needs to go away. There we go. The rate expressions is going to be the rate is equal to all of the different reactants and products related to their coefficients, and the coefficients are related by the fraction. So this is going to be 1/2 the concentration of hydrogen over time. So it's going to be the change. That's going to be equal to then the change in concentration of oxygen over the change in time. That's equal to then the 1/2 change in concentration of water over time. Now these are going to be negative for the reactants and positive values for the products. Now, since this is water, right, it doesn't make sense to have a concentration of a pure substance. So a lot of times when we see all gases here, we would do this as pressures instead. So we'd say rate is equal to the change in pressure of hydrogen gas over change in time. A equals, again, then the change in pressure of oxygen over change in time. I'm going to go back and fix some things here. Change in pressure of water over change in time, and this is going to be our 1/2. That'll be negative here. This is also going to be 1/2. So we can see that this is H2O instead. It's the same thing, just depending on what values you work with. Now, usually we're going to be dealing with concentrations, but I might throw a pressure in there just to keep you on your toes. All right, so letter B is going to be the exact same thing, so I'm not going to do that one. Number 7. suppose that at a particular moment in time during the reaction of nitric oxide, we have it's reacting at the rate of 0.066 molar per second. And we want to know what the rate of the NO2 is forming and what rate the molecular oxygen is being used. And we're going to be using that same stoichiometric relationship. So we have nitrogen monoxide is going to be 1/2 change in concentration of nitrogen monoxide over change in time. That's negative, and that is then equal to this thing right here. Negative 0.066 molar per second. So that's molar per second. That's a change in concentration over change in time. 0.066 is the value. Now, I don't want to forget that 1/2, and that is equal to our nitrogen dioxide first is also going to be 1/2 change in concentration over nitrogen dioxide over change in time. And this whole thing here becomes our variable that we're looking for. Since we have 1/2 of this, 1/2 of this, those things go away, and we're left with 0.066 molar per second. So molar is this piece here. Molar is right here. And then seconds is here. So there's how we get our values and our units for that. Now if we're going to be doing molecular oxygen, we would have negative 1/2 0.066 is equal to change in concentration of oxygen over the change in time. And since there's no fraction on this side, it just becomes half that, so it comes out to be 0.033 molar per second. All right, so there's that. Number 8 is the exact same thing, so I'm not going to do that one. And then number 1 on the next page, you see the numbering is off. That's because I've combined different worksheets, different practice problems from different locations. I didn't bother to renumber things. So this is going to be the exact same thing as number 6 here, right in the rate expressions. So I'm not going to do that one. And number 2 and number 3 are going to be more practice based on those coefficients. So I'm going to skip over those as well and go directly to learning objective 2, which is on the rate law stuff. All right, so the first thing here asks for what the overall orders of these reactions. Remember that the order is based on the exponent. Now, since there's only one reactant here, it's just based on that. So this would be second order. When we have rate is equal to K, that means that no matter what concentration we have of the reactant, it's not going to change the rate. And so this is going to be 0 order. Here, this is a weird one. We don't often see half values for our orders, but it is possible. So this comes out to be 1.5 for the order, and this is then third, 2, and there's a 1 there because there's no exponent indicates a 1, so that's third order. All right. Number 18 says the rate of the reaction is that thing there, 0.016, and the concentration of that reactant is 0.35. Calculate the rate constant if it's first order or second order. So I have two different rate laws I have to write. Rate is equal to constant times A raised to the first power, and then rate is equal to K raised to the second. And so we can plug things in. Rate is equal to 1.6 times 10 to the minus second K, 0.35. We do the exact same thing except we'd square that 0.35. We end up with our values of 0.046. And here's the unit for first order. 0.13 is going to be 1 over molarity times second. So we have that. So if we have we can do this real quick. Maybe if we have a zero order reaction, units are just going to be molarity over time. First order, it's going to be 1 over time. Second order is going to be 1 over molarity times time. Third order is going to be 1 over molarity squared times time. And that trend just continues for how many different orders you have. All right. What is the half-life of the compound if 75% of the sample decomposes in 60 minutes? Assume first-order kinetics. And there's like 3 different ways to do this problem. The way I like to do it, though, or the one I like is best, is just using the half-life equation. So I know it's first order, and based on that integrated rate law equation sheet I gave you, the half-life of a first-order reaction is the natural log of 2 over the constant. This comes out to be 0.693, so we end up with a half-life equal to 30 minutes. Oh, I see. Oh, we need a little bit more in this, don't we? Because we don't have a constant. Well, this is the way to do it then, because we need to get that constant. We could do natural log of 25 equals negative k times 60 minutes plus natural log of 100. Now this is the integrated rate law equation. So we have 100 for the initial concentration, 100% of it. We have 75% gone, so we have 25. And solve for the constant. The constant comes out to be 0.023, and that'll be minutes raised to -1. I'm going to plug that guy in. So I have this thing here. Now, it occurs to me that there's a much easier way to do this problem. So let's do that as well. If we have 100% of a compound, that is going to be at half-life number 0. If we have 50% of the compound, that's going to be half-life number 1. If we have 25% of the compound left, we have half-life number 2, and 12.5% would have half-life 3, and so on and so forth. And so if we have 25%, which is a nice whole number in terms of half-lives, we've gone through 2 half-lives. If we've gone through 2 half-lives and 60 minutes has passed, that means that 30 minutes is equal to 1 half-life. So that's an easier way to do it if you're dealing with numbers like 75%, 50%, 12.5%, things like that. Now, what we run into is if this problem, instead of said 75%, said like, I don't know, 63% of a compound decomposes, we could not do it this way because it does not decrease in a linear fashion. It's in between here somewhere, or excuse me, here somewhere. So we would have to go through this entire process, solve for the constant, plug the constant into the half-life equation, and then you'll be good to go. All right. Here's another one where we have half-lives and first-order equation. So in this problem, we have the half-life. It's 35 seconds at 680 degrees. Now, we talked about this in class. This is something that a lot of students get confused about. We have a temperature here we don't need to do anything with the temperatures. Just remember that we need a temperature to describe the constant, because if we change the temperature, the constant also changes. So have the half-life, calculate the first order rate constant. There's some formatting issues. Calculate the first order rate constant and the time required for 95% of this thing to decompose. So we have rate is equal to the, oh, what am I doing here? Yeah, oh, I'm right in the right, there we go. Constant times pH3. Sorry about that. We have the rate law equation, so that's what I wrote out there just to make sure. So we're looking for, just to have that. If we want to figure out the rate order constant, though, we can use the half-life equation. T1/2 is equal to natural log of 2 divided by k. We have 35 seconds, 0.0693 over k. So k is equal to 0.0198, 1 over seconds. Now we can plug it in. So this is just like the problem we did before, only we can't do it by half-lives. So we have natural log of a at some time is equal to negative k t plus. All right, and so now we can plug things in. We're looking for the natural log at 5% because 95% of it's decomposed equals negative 0.0198 t plus natural log of 100. We end up with t equal to 151.3 seconds. So there we go. All right. Number 28 is very, very similar, only a couple differences here. First, we don't have any half-lives that we're working with, so it's just straight using the integrated rate law equation, and we don't have any kind of, and it's a second order reaction. So instead of using the natural log stuff, we're going to use the inverse. So we have 1 over concentration of reactant at some time is equal to the positive constant time. Then we have plus 1 over the initial concentration of the reactant. So we have the rate constant, which is 0.54, and we have the concentration to start with and to end with. So all we're looking for is time. So we have 1 over 0.28. The constant is 0.54. 1 over the initial, which is 0.62. We end up with the time equal to 3.63 seconds. And there we go. All right, so now we are looking at, we're going away from the integrated rate law and looking just at rate law work. So what is the rate law? What is the value for the units of the rate constant? So all of these questions are going to be the same thing. And I'll only go over, I think, 2 of them is all. So first of all, what is the rate law in this case? It's going to be rate is equal to NO raised to some power Cl2 raised to another power. So rate is equal to, well, let's do it this way. let's look at trials 1 and 2. When we look at trials 1 and 2, we see that the nitrogen monoxide concentration doesn't change, but the chlorine concentration doubles, and the rate also doubles. So if we look at the equation, if the nitrogen monoxide stays the same, this no longer is part of the rate law, and the constant isn't part either, so we have rate is equal to this to the raised to the y power. And you just plug things in. 2 in for chlorine, 2 in for the rate, so we say 2 raised to what power equals 2, and that means that y has to equal 1, 2 raised to the first power equals 2, so we have y is equal to 1. We can do the exact same thing for the nitrogen monoxide, except now we're going to look at the other two. And boy, just didn't use enough colors, so we'll do green and red. All right, so if we look from here, chlorine is constant. We have a double here. This goes up by a factor of 4. That means that 2 squared is equal to 4. Therefore, the value for x right here, which I kind of crossed out, is going to be 2. And so we have rate is equal to the constant concentration of nitrogen monoxide raised to the second power. There's the second power. Chlorine raised to the first power. So that is the rate law. This is A. Now if we look at B, we have the value of the units for the rate constant. We can just plug values in. So I can just use any of these that I would want. I'm going to use the first experiment. So I have rate is equal to 0.18 equals constant. Then we have 0.1 squared and 0.1. So I'm plugging things in here, 0.1 squared, 0.1, and K comes out to be 180. And the units for this guy are 1 over molar squared times second. So we'll look at that. Rate is equal to molarity, oops, this is minutes. Molarity per second, that is rate, is equal to constant. Now we have molarity cubed. I'm opening this parentheses because we have the MO squared, Cl2, molarity squared times molarity is molarity cubed. And if we divide the molarity cubed over, K comes out to be 1 over molar squared times second. And there you go. So that's how you get the units. So there's units. And now we have the value. And we have all the work. All right. I'm going to skip number 2. I do want to say that if I forget to tell you guys in class, the handout that you currently have that I'll fix for subsequent years does not have this column in it. And that is something you need in order to be able to do this problem. And so if you're working on that problem on your own and you're coming to the video right now trying to figure out what's wrong because you can't do it, it's because you're missing this data. All right. Number 4 is the one that I want to do. This one is a little bit tricky. first of all, let's write out the rate law again. We have I don't want red. Rate is equal to, we have the iodine raised to the x, and we have the COCl raised to the y. I forgot the k. So there is the rate law. Now I have to figure out those exponents. One of these exponents is going to be easy to get, the other one not so much. So if we look at the one that's going to be easy to get, it's going to be the iodine. So I have two different places where those are constant and two different places where these are constant. So I have either of those to really choose from. Now 0.24 and 0.03 aren't a nice multiple of each other, but 0.06 and 0.12 are. This is a multiple of 2. That's constant, and this is a multiple of 2. So that means that our I has to be our raised to the first power, so x is equal to 1. Now I have to figure out what y is. We can look at a couple different reactions here, and I'm going to look at 2 and 3. Now the reason I'm going to look at 2 or 3 is because they have nice values to them. This one doubles here. Oops. This one doubles. I use a different color. This one doubles. And then this one also doubles. And then this goes up by a factor of 4. 0.0395 divided by 0.00988 is going to give you a multiple of 4. Now if I have the rate is equal to 4, we can get rid of constant. I is 2 raised to the first power, and then we have 2 raised to the y power. I now have something I can simplify into 4 is equal to 4 raised to the y, and y becomes the first power. So this one is a little bit more difficult to go through because of no consistent information on the iodine concentrations. But if you start to break it down into its math components and look at some easy whole numbers to work with, it is possible to deduce what that other subscript or what that other power is going to be based on substituting things in. So there's that. All right. How are rates affected by concentration? Well, this is a pretty easy one. As we increase concentrations, we increase the rate of reaction. And that's going to be true for all kinds of reaction rates other than zero order. Zero order reactions are special, and no matter what you do with the rates or the concentration, the rate is not going to change. All right. Why does this look a whole lot easier than it should be? All right, a reaction obeys this. What are the orders for A and B? A is going to be 1, and B is going to be 2. The overall order is going to be 3. That's because this is, see how it restarts the numbering? That means that I got it from a different practice sheet that I've put together, and so you might see some varying difficulties as you go through these worksheets. Which is fine. It keeps you thinking in a nonlinear fashion. So we have that. All right. So number 3 is going to be like problems we've done before. That is the 3:15 bell, ladies and gentlemen. So there'll probably be some noise in the hallway as people are leaving. All right, the rate law for this is going to be and it says it's first order for each reactant, so 1 and 1 there. And so now we can plug things in. What is the rate constant? Very simply, ladies and gentlemen, we plug things in. 0.0432 is equal to the constant, and then we can plug in the concentrations. The methyl bromide is 0.005, and the hydroxide is going to be 0.05. K comes out to be 172.81 over molar seconds. There's that. Number 5 is going to be the exact same thing. We're just going to be dealing with a first order reaction here where we have the constant and we have some concentrations. So the concentration of 0.024 and 0.048. So we have the just two different problems here related to that one reactant. I'm not going to go through the problem for this, but I will go over the answers. The first one is going to be 1.16 times 10 to the minus 4th molar per second. That's not right. It's, oh yeah, that's that is the rate. I'm sorry. Thought that was the rate law. Molar per second, and this one is going to be 2.31 times 10 to the minus 4th molar per second. It's just doubled because the concentration is getting doubled. That's the rate. So you're plugging in for the constant. You have the constant, plug that in, and solve for the rate. All right, number 6 is going to be integrated rate law work. We have a first order reaction with a half-life of 25 minutes. And then we can use that constant that we get to figure out time in the other two equations. So we have, oh, and these are the answers over here. So we have t1 half is equal to natural log of 2 over k, and that's going to be equal to 25 minutes. Oh, this is another one of those that we could do without the equation. So I'll show you how to do that one and this one with the equation. This is kind of a nice problem. We get to see a couple different things. So the t1 half is 25 minutes, which means the constant comes out to be, that guy up there, 0.0277 minutes. Raise the negative first power. So letter A, do A here, or B, I'm sorry. Here's B, here's A. B, we could do it this way. We have 100% at some time. We have 50% at some time. We have 25% at some time. Now we know that the 25, or excuse me, we know that the 100% is at 0, so there's no time passed. At 25 minutes, that's our half-life. 50% is decomposed into something else. And then at 25, we have 50 minutes, because each half-life takes 25 minutes. So since this 75% decomposed is 75 or complete, so we have 25% left, we have just a way to use a table to figure out the overall time of 50 minutes. Now, instead for letter C, we have 35%, which does not fit into a table, and since it's not linear, we can't use this method to figure it out. We have to use this natural log of the concentration of time is equal to negative constant times time plus natural log of the concentration of the reactant initially. So we have natural log of 25 equals negative 0.0277 t plus natural log of 100, because that is the initial. So that 0 there means initial. The t here means at some time, and that's what we're trying to solve for. We have 25% left after 70, or excuse me, should be doing this with this one. Oops. 65, because we have 35% complete. This is letter C. And we can plug everything in. We end up with the time is equal to, oh yeah, 16 minutes. That's right here. Derp. So there you go. All right, erase here, click through. Number 7 is the same thing, only it is going to be a second order reaction. So instead of using the natural log equation here for the half-life, you'd be using the 1 over. So the T1/2 is equal to 1 over the constant times the initial concentration. So we can plug those things in. We have 143 seconds is equal to 1 over the constant times the initial concentration of 0.060. We end up with a constant equal to 0.12. Yeah, and different units here, guys. There's a lot of, well, not a lot of, 3 different ways you can express units. Like this unit here, since it's second order, is molarity raised to -1, second raised to -1, or this is the exact same thing. And since molarity is equal to moles per liter, we could then, and then molarity is on the denominator, this would end up as liters per mole seconds. So it just depends on how far you break down the units, because molarity is defined as something as well. So you can see that we have different ways of showing those units. All right. Number 8, we have the decomposition of hydrogen iodide, and it is 0 order. So that is an important piece of information here. It is 0 order reaction. And we have the rate. Now it looks like this is times 10 to the -4th up here. And moles per liter second will be the same thing as molarity over seconds. So that's the 0 order. Assuming that the concentration versus time data were collected, sketch what it would be. Well, we have time here on the y-axis, and we're going to do concentration of the hydrogen iodide. Now, since it is 0 order, that is a linear relationship. Ooh, hold on. It is a linear relationship, but it's going to be negative. So this guy should actually look like this. That would be the correct graph. All right. The initial concentration is 0.250. Calculate the concentration at 25 minutes. We have our concentration of something at a given time, negative constant times time plus the concentration initial. So that is the 0 order integrated rate law equation, and we just plug things in. We have 25 minutes here. How long would it take for, oh, I'm sorry. I'm on the wrong problem. Yeah, here, now I got it. So we have concentration of hydrogen iodide is equal to the constant, which is 1.35 times 10 to the -4th. plus the initial concentration of 0.25. Sorry about that, guys. Just a little fuzzy right now with getting over this cold here. So we're solving for this concentration. Just plug things in. So here's the integrated rate law equation for the zero order. Here's what I'm solving for, the concentration at some given time. That time is going to be at 25 minutes. So here is 25 minutes. And just do all the math. We end up with a concentration of 0.05 moles per liter. All right. Well, I almost feel like I need to go back and do that one again. But I'm not gonna. Letter C is the same thing, only now we're going down to 0. So we have that same integrated rate law equation. We end up with 0 here. We have the 1.35 times 10 minus 4th some time plus, and we started with 0.25. Solve for time. That gets us 1,850 seconds. So there's that. Whew. All right, so that's all of Learning Objective 2. We're going to be doing a lab Learning Objective 2 and looking a little bit more at graphs as well. So make sure that you do not just limit your total understanding of Learning Objective 2 just from this. There'll be some other stuff that you want to make sure you review as well. All right, Learning Objective 3. Activation energy is the amount of energy required to start a reaction. Without it, the reaction does not start. Therefore, you cannot have any chemical kinetics. So that's why that's important. And we have number 1338. There's a couple different equations for this. The Arrhenius equation is what it's called. And if we are dealing with a problem like this where we're trying to figure out something at 2 different temperatures, we're using this one. Natural log of constant 1 over constant 2 is equal to the activation energy times the R constant. That is an R, guys. Activation energy R. Ooh, something looks wrong here. Over R. One over T2 minus 1 over T1. Let's try this again. Natural log K1 over K2. There we go. Is equal to this whole thing here. Now, a couple of things to note. We're dealing with two different reaction constant, rate constant, and that's because we have 2 different temperatures. Remember, we've said several times now that the rate constants will change based on the temperature. And so if we have different temperatures, we have to correspond them with different constants. So this is the constant at this temperature, and this is going to be the constant at that temperature. So we can just plug things in. Now we have natural log of K1 over K2. So the one at 250 degrees Celsius is 1,500 times faster than the one at 150 degrees Celsius. We don't have one for 150 degrees Celsius. Now that doesn't matter because the fraction is going to be 1,500 over 1. So it's going to be a natural log of 1,500. It's equal to the activation energy, which is what we're looking for, over R, 8.314. I know I have to use this version of R because I am dealing with energy, which is in joules. So we have 1 over 423 and 1 over 523. A couple things here. We're using our T2 here, which is going to be our 150. Have to convert that into Kelvin. So T2 is going to be the smaller value, and T1 in this case is the larger value. I have to make sure that corresponds correctly to my equilibrium constants. Now, if I would have done this upside down and say did 1 over 1500, so 1500 is related to K2, I'd have to switch these two values around to make sure that it matches the correct constants. All right. And now I can just do my math. I end up with an activation energy of about 135 kilojoules. Now, when you get a value in your calculator, it's probably going to be close to 135,000. Remember, ladies and gentlemen, that this 8.314 is in joules per mole Kelvin. And so all I did was change it in kilojoules because those are nicer numbers. All right. 39, we have a frequency factor. Now, if we have a frequency factor, we're dealing with a specific activation energy at a specific temperature and not comparing two different equilibrium constants. For example, here we had two different constants we're looking at. In this one, we're just going to be looking at one constant. And therefore, we use the original Arrhenius equation, which is going to be equal to, I don't want red. K is equal to, capital A is going to be the frequency factor times lowercase e, as in the opposite of natural log, raised to the power of the negative activation energy divided by R times T. We'll just start plugging things in here. K is equal to 8.7 times 10 to the 12th. Now the frequency factor is based on how often the collisions occur and some other things that go into it, but this is something that has to be given to you. It's not something that you would have to know or look up or anything. It has to be part of the problem. The only other exception here is if you're given the constant and everything else and asked to solve for the frequency factor. So there's that, times E raised to the activation energy. Now this is where we want to make sure that we do things correctly. It's going to be negative 63,000 because it's in kilojoules here. I want to make sure to convert it into joules, divided by 8.314 times that temperature, 75 Celsius, is 348 in Kelvin. So our K comes out to be 3.0 times 10 to the third over second. So it's first order reaction. All right. Number 40, the rate constant is this thing. The activation is this thing. Calculate the temperature. If the rate constant is that. So this is going to be the same thing as question number 38, only we're looking for a different variable. So in this case, we're going to do natural log of 4.6, and my 4's always look so crappy, 4.6 times 10 to the minus 4th divided by 8.8 times 10 to the minus 4th equals, now we have the activation energy. I'm doing this problem out because I want to make sure I show you this here, 1,000 joules over 8.314, 1 over the first temperature, excuse me, the second temperature is what we're looking for, and 1 over 623 for the other one. We have temperature 2 is going to equal 371 degrees Celsius. So, and I converted it into Celsius here from Kelvin. So make sure that if you get a weird number in the 500 range, you understand that that's in Celsius. All right. The other part of this section is the how we relate the mechanism of a reaction to the rate law of a reaction. And it has to do with the slow step of the reaction. So if we look at question number 51 first, we have this overall reaction here and a rate law here. And we want to know some information about where the exponents come from. Well, the exponents come from the slow step of the mechanism. So this is supposed to be lowercase 2. These two different steps are observed during the reaction. So this is the overall reaction. These are the two individual steps. And the slow step is going to correspond with the rate law. Now, I'm going to explain what that means here in a little bit, but the point that I want to make before I go back to question number 48 is that there's two or more different individual steps in a mechanism. Now, we don't get really in depth in mechanisms of reactions. They do get very important in, say, organic chemistry. But right now, we just need to know that there are different steps, and one of them is going to be the slow step. The slow step determines the rate of the reaction. And if you imagine like some containers here, there's a container here, and that's connected to another container here. And then that's connected to yet another container here. And then we have a container, another container, something to dump this in. So what I'm doing is I'm pouring water in this. So in comes water. Here's my H2O. And it fills up this container here, then it funnels into this container, funnels into this container, funnels finally into the receptacle at the very end. It doesn't matter anything about these two steps and how fast this water can be dumped through these containers, because this area right here, this funnel or this connector is smaller than these. And so this connector here is going to determine how fast we can fill up the end receptacle. So this is what's called the rate determining step, or the slow step. And that would be kind of a real everyday scenario. Just a regular scenario would just be just one single funnel, because the diameter of the funnel determines how fast you can pour stuff into it and into the container below. Another one would be a traffic jam, where we have cars coming in onto an interstate on the entrance. So those are different ways to determine or to show the slow step. Now down here, this one, the slow step matches the rate law. And so since the rate law looks like this, those are exponents of 1, we have two different steps. We have a coefficient 1 here, 1 here, 1 here, 1 here. The products don't matter because they're not involved in the rate law. If we look at this right here, the coefficients 1 and 1 match the rate law. So this is when the coefficients do match the rate law. When we break it down into the mechanisms and we identify which one of those individual elementary steps matches the rate law. And what that tells us is that this is going to be the slow step. That is the rate determining step. All right. We're on objective 4. Catalysis. So a catalyst decreases the activation energy of a reaction, allows it to proceed more quickly. So if we look at two different graphs, here is one reaction with the activation energy and products. So this is relative energy, and this is time. We have another one here, which looks like this, where we have something like that. Here's time again. Energy. This is going to be the catalyzed reaction because it decreases the activation energy. So here's the activation energy here. And here's the activation energy here. All right, so that's how catalysts work. And we have two different kinds of catalysts. We have a homogeneous catalyst and we have a heterogeneous catalyst. The homogeneous catalyst is going to be one of the same phase, and the book gives this example of ethyl acetate breaking down into ethanol and acetic acid. But the heterogeneous ones are a lot more, explain a lot more detail and have some specific examples that are very, very important. But it is different phases. So we have a solid and a gas or solid liquid together. We have that. Now, in this case, the Auber synthesis of ammonia is super important in terms of chemistry because ammonia is used in agriculture as a fertilizer. And without this reaction, without this catalyzed reaction, we would not have agriculture the way we do right now. And so it's super important for feeding the world. So there's that one. Go chemistry. Catalytic converters are found in cars, and it helps limit the exhaust that comes out, the harmful pieces of exhaust that comes out of your car. So that's all learn objective 4 is the catalysis. All right, ladies and gentlemen, hope that was okay. Again, working with a cold right now, so hopefully I didn't space off too much during that thing and it made some sense. Like I said, for those problems that I didn't do in class, please feel free to come in and see me for that. All right?